This lecture is the second talk in a 5-part series about EEG montages. This section deals with bipolar montages. I will start this section using the question and answer format that I have used in the past. First question: which of the following montages is characterized by a series of multiple derivations connected with each other in a straight line? A. Common reference. B. Laplacian. C. Bipolar. D. Average reference. A bipolar montage consists of a series of multiple adjacent derivations connected in a straight line and arranged in a chain-like fashion, with the electrode going to input 2 of a differential amplifier being the same electrode as the one going to input 1 of the adjacent amplifier. Bipolar montages are either longitudinal or transverse. Longitudinal bipolar montages go from front to back. Transverse bipolar montage go from left to right. So the answer to this question is C, bipolar. Next question. A longitudinal bipolar montage is a series of adjacent derivations connected with each other in a straight line going from front to back. A true, B false. This frame shows a typical longitudinal bipolar montage. It goes anterior to posterior, with left on top and right on the bottom. So the answer to this question is A, true. Next question. A transverse bipolar montage is a series of adjacent derivations connected with each other in a straight line going from left to right. A true, B false. This frame shows a transverse montage. On top we see FP1 to FP2. Below we see from F7 to F8. Below that we see from A1 to A2. Below from T5 to T6 going through PZ. And just below that we see going from T5 to T6 but going through the occipital region. So the answer to this question is true. Next question. A single phase reversal in a bipolar montage indicates a change in polarity of the potential. A true, B false. The highlighted area constitutes a reversal in the phases of a wave. The T4 T6 channel and the T6 O2 channel show deflections that point towards each other. T4 T6 channel points down and T6 O2 channel points up. This is called a phase reversal. In bipolar montages, the electrodes involved in the phase reversal, whether the deflection points to each other as in the case I just showed you, or away from each other as in other cases, indicates the location of either the minimum or the maximum of an electrical field. It does not indicate a change in polarity of the field. Because of this, since the term of phase reversal is also used to indicate a change in polarity, the word instrumental is added to the term phase reversal when a phase reversal is present in a bipolar montage. When the deflection in an instrumental phase reversal points towards each other, the common electrode lights on the generator. In almost all cases, the potential below the common electrode is the maximum negativity of a negative electrical field. So the term negative instrumental phase reversal is often used to describe this type of phase reversal. Although, at least theoretically, when an instrumental phase reversal points towards each other, it could also represent a minimum positivity of a positive electrical field under the common electrode. On the other hand, if the sharp activity is going in the opposite direction, that is, away from each other, as in this frame, the term positive instrumental phase reversal is often used. Again, from a theoretical point of view, a field with a minimal negativity at the common electrode could also produce the same finding as I just previously described with negative instrumental phase reversals. But again, such a geometry defies the common laws of physics. So the answer to this question is false. Next question. The highest amplitude in a particular channel of a bipolar montage indicates the site of the generator maximal voltage. A true, B false. This frame represents a longitudinal bipolar montage. In it, I have just included the representation of a field. On top, I have presented the same field but given a voltage value to each color. On the side, I have represented the waves corresponding to each derivation. Notice that the tallest wave is not arising from the area with the highest voltage, but from the area with the steepest voltage difference. So the answer to this question is false. Next question. Bipolar montages are good for detecting low to medium amplitude, highly localized waves. A true, B false. I will start answering this question by introducing, or that is reintroducing, the amplitude area chart that I show you in the first part of this talk about montages. I have done so to indicate the potentials better detected when using bipolar montages, which are those that are low to medium amplitude and highly localized potentials. These low to medium highly localized potentials produce an instrumental phase reversal that are very easy to notice. So the answer to this question is true. Next question. In analog EEG, the electrodes at the end of a chain are subject to increased artifact, but this does not occur using digital EEG. A true, B false. Using analog EEG machine, a bipolar montage is more likely to have artifacts in the derivations arising from the beginning or the end of a chain. Then in the in-between chain electrodes. This is because the first and the last electrodes in a chain are only connected to one amplifier and thus to only one ground. Whereas all the electrodes in the chain are connected to two amplifiers and therefore two grounds. That is all the electrodes in the chain that are not the first or the last. This phenomenon does not occur with digital EEG, since with digital EEG all electrodes are only connected to one ground and the bipolar montage is reconstructed by mathematical computation. So the answer to this question is true. Next question. If two bipolar chains of electrodes share the same electrodes at the beginning and at the end of the chain, the sum of the deflections of each chain will always be identical. A true, B false. This frame represents a bipolar montage consisting of two chains of electrodes joined at the beginning and at the end of the chain. In such a situation, the sum of the deflection of each chain, that is, in this case, the temporal running chain and the central running chain, both add up to the same voltage, in this case to positive 78. So the answer to this question is true. Next question. The spatial analysis of the distribution of EEG potentials can be represented by A. Voltage electrode position graph, B. An isopotential map, C. A polarity graph, D. All of the above. The spatial analysis of the distribution of an EEG potential can be represented by an isopotential map, a voltage electrode position graph, or a polarity graph. So the answer to this question is D, all of the above. Next question. When calculating a polarity graph using bipolar montage, each electrode is connected with its pair by a direct line. A true, B false. A polarity graph consists of a chart with polarity in the y-axis and electrodes in the x-axis. The polarity of each electrode is then placed in line with the electrodes. When representing a bipolar montage, each electrode is connected with its pair by a direct line reflecting the positivity or negativity of the first electrode in relation to the second electrode, and so on. The amplitude is not taken into account. So the answer to this question is A, true. Next question. When calculating a voltage electrode position graph using a bipolar montage, the arrows indicating amplitude go between the electrodes. A true, B false. I will use this example to explain the making of a voltage electrode graph. Here I have added arrows with the head of the arrows in the direction of the wave and an amplitude equivalent to the size of each wave. In this frame, I am introducing the presence of a voltage electrode graph. Notice that the voltage is represented between the electrodes and that the amplitude of the chart graph reflects the amplitude of the electrodes. So the answer to this question is true. The epoch above belongs to which of the isopotential maps below? Let's first analyze the A choice. The first step when analyzing an isopotential map is to create a polarity graph as I have done in this frame. In it, we will represent each electrode according to their relative polarity. A more negative electrode will be placed towards the top, and a more positive electrodes will be placed towards the bottom. We will start by plotting the electrode closest to the maximum of the electrical field. In this case, the green electrode. The electrode location of the green electrode is at the beginning of the polarity graph since it is the most anterior electrode. The location of the electrode in relation to the chain establishes its x-axis localization. It is its relative amplitude that establishes its y-axis position. Then we go to the next electrode, in this case the yellow electrode. You can see that the green and the yellow electrodes are both at the same potential line. Hence, there is no gradient between them. This is represented by placing the yellow electrode at the same level as the green electrode. This is expressed in the chart by a horizontal line between them. Next, the activity being at the same voltage level do not create a deflection in the channel from these electrodes. Next, we look at the yellow and the magenta electrodes. These electrodes are at different potential levels. The magenta electrode is at a more positive level than the yellow electrode. This will be represented in the voltage graph by placing the magenta electrode one level towards the positive signs and drawing a line between the yellow and the magenta electrodes. In the epoch I will represent this as an up deflection in the corresponding channel because the electrode at input 1 of the derivation is negative in relation to the potential coming into input 2. Next, we look at the magenta electrode and the aqua electrode in the isopotential map. Since they both are at the same voltage potential, we will place them at a straight line between them. In the epoch, since the magenta electrode was labeled positive and the aqua electrode is at the same level, the aqua electrode will also be labeled positive. Such pair will therefore produce no deflection. Finally, both the aqua and the blue electrodes will be compared. They are at the same potential level, thus we will place a horizontal line between them, which will be projected in the epoch as a channel with no deflection. Please take a few seconds to look at this configuration in the lower part of your frame. So we have finished our analysis of sample A. And we will start now the analysis at sample B. We first look at the map and build a polarity graph starting by placing the electrodes closest to the maximum of the field at its corresponding place in the chart and its corresponding polarity. Then going to the next electrode frontally, we place it in the appropriate electrode position and appropriate level. We then do the same we did in the prior discussion and go to prepare the corresponding epoch by arranging each channel according to its input. Once sample B is analyzed, we do the same thing for sample C. We look at the voltage isopotential map. We develop a voltage graph following the previously stated order and produce the corresponding epoch. So the answer to this question is B. Next question. The epoch above belongs to which of the isopotential maps below? Please take a few seconds to look at this cartoon. You can figure out the answer to this question by just looking at this frame. You start by placing the electrode closest to the maximum of the field, and as if it is in this case that there are two, you choose the most anterior one to start. Then you place it at the corresponding electrode position and potential level. Next step, you analyze the magenta electrode and place it in the corresponding position and voltage level. Since both are at the same level, you join them by a horizontal line. You draw the corresponding channel showing no deflection in the epoch. In this case, it will be the second channel. You then do the same with the green electrode and compare it with the yellow. It is very important for you to remember that you always need to compare the anterior electrode with the posterior one while building a voltage graph. This is so when you are building a voltage graph for a bipolar montage. In this case, where the bipolar montage is longitudinal, if you were analyzing a transverse montage, then you compare the electrode on the left to the electrode on the right. The bottom line is that although the value of the polarity that is negative or positive is ruled by the relation between input 1 and input 2, the direction of the wave is dictated by input 1. Next, you go to the magenta electrode. The magenta electrode is more negative than the aqua electrode, thus producing an up deflection. Then you analyze the aqua electrode. The aqua electrode is more negative than the blue electrode. The channel from this derivation will also show an up deflection. So the answer to this question is C. Next question. The epoch above belongs to which of the isopotential maps below? This frame includes the tracing cartoon, the isopotential map, and the polarity graph corresponding to option A. This one shows the same representation for option B. Please take a moment to review them. And this one for option C. Again, take a few seconds to review it. So the answer to this question is B. Next question. The epoch above belongs to which of the isopotential maps below? Stop the video at this point if you have to and try to find the answer. I will briefly present to you a summary frame. The important point that I would like to make at this junction, since we have already worked up all this probability in prior question, is to emphasize that the polarity of the first electrodes, or the first electrode outside the field, in this case the magenta electrode, dictates the polarity of all electrodes outside the field. So since in this case the polarity of the magenta electrode is positive in relation to the yellow electrode, all other electrodes outside the field are labeled positive in order to complete the epoch. So the answer to this question is A. Next question. The epoch above belongs to which of the isopotential maps below? Take a look at this frame. Remember that to build a potential graph, you have to start with the electrode representing the maximal of the field presented. In this case, the blue electrode. Then the electrode should be placed at the appropriate position, in this case, the fifth electrode position, at the appropriate level that is most negative. Then you look at the closest electrode to the one you just placed. In this case, it is the aqua. But at the time of drawing the corresponding channel, you have to look at the anterior electrode first and draw the channel deflection according to the polarity of the most anterior of the pair. That is the one that is going through G1 of the amplifier. So the answer to this question is A. Next question. The epoch above belongs to which of the isopotential maps below? This frame shows the solution. So the answer to this question is C. Next question. The end of the chain phenomenon refers to the situation that occurs when the potential arising from the end of the chain derivation has the highest amplitude. A true, B false. This frame shows two isopotential maps with the maximal polarity in the posterior regions. Their corresponding tracing are above them. This frame shows two isopotential maps with the maximal polarity in the anterior regions and the corresponding epoch above them. The point is that when in a bipolar montage there is no phase reversal, the field maximum is located under either the first or the last electrode of the chain. As you can see in this example, the actual site of the source, anterior or posterior, is determined by the amplitude of the potentials on the side of the highest potential. The highest potential does not necessarily needs to be in the first one electrode of the chain, as it is not in this example. Remember that in a bipolar montage, the height of a potential is dictated by the voltage steepness between the electrodes and not by the absolute amplitude of the potential. I also would like to remind you that the term end of the chain phenomenon is also used to denote the increased propensity for artifacts in the distalmost electrodes of a chain in a bipolar montage when analog EEGs were used. So the answer to this question is A, true. Next question. A phase reversal at one location in a longitudinal or transverse bipolar montage allows localization of a focus maxima. A true, B false. This frame shows an isopotential map, a tracing cartoon, and a voltage electrode graph. Please pay special attention to the isopotential map. Notice the position of the electrodes in relation to the voltage source. In this frame, the magenta electrode is right on top of the source. Now look at this new frame. The only change that has taken place in the isopotential map is that now the voltage source is to the left of the magenta electrode. But also notice that neither the tracing nor the polarity graph have changed. The same occurs in this new frame. When the maximal in the isopotential map has changed, as you can see, the magenta electrode is now to the left of the maxima, but neither the tracing nor the polarity graph has changed. In this frame, I have placed the three isolated isopotential maps we have just considered. In this frame, I have added a polarity graph that corresponds to all three isopotential maps and given them a letter in order for us to recognize them later on in the talk. And the later on is now. You can see now in this frame that I have aligned them under a white line. And above them, I have placed a miniature voltage electrode position graph. This graph corresponds to the one I have shown you before. As you can see, the maxima in this figurine is arising from under C. In this new figurine, the voltage graph has not changed, but the epicenter of the field is not right under electrode C, but C is still the electrode most involved. The same can be said about this new added figurine. The point of all this being that using a single chain of bipolar montage, the epicenter of a field cannot be determined. Now I have introduced a new set of electrodes at a right angle of the C electrode in the figurine on the left. Now I have done the same on the middle figurine, and now on the figurine on the right. Each of these chain electrodes will produce their own polarity graph. The first one below the left figurine, the second one below the middle figurine, and now one on the right figurine. I hope that this frame demonstrates to you that in order to precisely localize a generator using a bipolar montage, we must use longitudinal and transverse montage. Please take a few seconds to look at this frame before going to the next one. So the answer to this question is B. Next question. A phase reversal indicates the site of the source if the phase reversal occurs in the same electrode in another bipolar montage taken at right angle of the initial one. A true, B false. The presence of a phase reversal in a bipolar montage indicates that the maximum is under the electrode recording it only if a transverse strip at right angle confirms it. It doesn't have to be necessarily a transverse strip confirming a longitudinal strip. It can be the other way around. As you can see in this frame, there is a common electrode. On the other hand, if the phase reversal does not take place in the same electrode, or if the electrode is not included in the chain, as it is in this case, where electrode 3 is not included in the transfer chain, no precise comment can be made about the localization of the generator, as it is in this case. So the answer to this question is true. Next question. The epoch above belongs to which of the isopotential maps below? This frame shows isopotential map A. As you can see, it has two generators. It corresponds to the tracing pointed by the arrow and to the voltage graph also pointed by the arrow. Remember, when creating the tracing, that the polarity of the electrode pair should be arranged depending on the polarity of the input 1 in relation to the polarity of input 2. I have expressed this by the circles with the polarity signs by the side of each channel. The tracing, despite being generated by two voltage sources, has only one instrumental phase reversal, a fact that can also be noted in the potential graph. Such situations occur when one of the generator maxima is recorded at the first or last channel of a chain, or, as it is in this case, when the maxima is at an equal distance from each electrode at the end or the beginning of a bipolar chain. This frame shows an isopotential map for B. That was the second choice in the question. It also has two generators. Also presented in this frame is the corresponding tracing and voltage graph. If you look at the tracing, you can see a double instrumental phase reversal. And in the potential graph, you can see a voltage potential change. One voltage reversal occurs at the yellow electrode and another one occurs at the aqua electrode. In this frame, I am representing the C option of the core in question. As you can see, it has two generators too, but the maxima is at one end of the chain. Thus, the tracing will show no phase reversal, and no phase reversal will be present in the voltage graph. So the answer to this question is B. Next question. The presence of two generators of opposing polarities should be considered in which of the following situations? A flat N channel and a phase reversal in the same chain. B, two phase reversals in the same chain. C, the last channel with highest amplitude and a phase reversal. D, all of the above. This frame shows three isopotential maps and their corresponding potential graph. They, as you can see, that is, the isopotential maps all have two generators of opposing polarities. As previously discussed, this situation may arise in the presence of a phase reversal and a flat channel at either end. That was option A. It also may occur in the presence of two phase reversals. That was option B. Or in the presence of a phase reversal and the highest amplitude at one of the N channels. That was option C. So the answer to this question is D. The above tracings represent bipolar longitudinal montages. Which of them indicate a horizontal dipole, A or B? This frame has an isopotential map, a tracing, and a voltage graph corresponding with option A. This new frame has similar elements corresponding to option B. Please take a moment to think about this and then go ahead and answer the question. The answer to this question is A. Next question. An EEG with two distinct simultaneous maxima, one negative and one positive, can occur in a bipolar montage in all of the following situations, except A, a horizontal dipole, B, a simple vertical dipole arising in the crest of a convolution, C, a synchronous bilateral independent vertical dipole. D. A vertical dipole with a spread to the opposite hemisphere. The classical origin of two simultaneous distinct maxima is a horizontal dipole. The solid angle theorem provides a simple explanation for this phenomenon. Look, from each electrode perspective, the potential will be opposite, as you can see in this frame. This frame illustrates that the potential one created on each side will move in opposite directions. And in this new frame, which I have added the representation of the negative field and positive fields in order to make it more clear, or to make it clearer. This situation occurred with generators in the cortex adjacent to the internal hemispheric fissure and in the cortex of one wall of a fissure, but it can also occur when it is the wall of any convolution is involved. A dipole arising in the crest of a convolution, that is option B, behaves like a monopolar generator since only one side of the dipole is viewed by the overlying electrodes. But this may lead to an EEG with two maxima if two synchronous vertical dipoles arise from opposite sides occurred at the same time. Such situation is very rare, and usually scrutiny of the onset and peak of the wave will show a slight difference between the two potentials. A third possibility is that the dipole gets transmitted to the opposite side of the brain and therefore creates a field on the other side, that is on the opposite hemisphere, because of crossover. This situation, that is the transmission of one side of the dipole to the opposite hemisphere, usually occurs in very rare occasions in the temporal lobe. So the answer to this question is B. A bipolar longitudinal montage is needed to verify interhemispheric asymmetry noted in a transverse longitudinal montage. A true, B false. Asymmetries are usually not detected in longitudinal bipolar montages. They are usually detected using transverse bipolar montages. The absence of an asymmetry in the bipolar montage, that is the absence of an asymmetry in a transverse bipolar montage, is a reliable indication that no asymmetry is present in the tracing regardless of whatever montage we use. So the answer to this question is B, false. Next question. Channel 5 and channel 6 show a phase reversal. True or false? The activity in channel 5 and 6 can be misinterpreted as an instrumental phase reversal. This is not the case. 2 points suggest this conclusion. The two waves have dissimilar shapes, and the timing is slightly off between them. So the answer to this question is false. Next question. Which of the following situations is likely to be misleading using bipolar montages? A. Very uneven voltage gradient. B. Equipotential zones at the end of a bipolar chain. C. Monotonous recording. D. All of the above. As we have already heard, bipolar montages interpretation presents some pitfalls. One of the pitfalls when reading a bipolar montage is to assume, without room for doubt, that a large amplitude potential at the beginning of a chain indicates the presence of a maximal under the electrode capturing the high voltage potential, when, although less likely, we may be dealing with an uneven middle of the chain maxima field. Let's look at an example. This tracing can be interpreted as a positive field with maxima positivity in the frontal polar electrode, where we to place electrode at the location shown in this frame, that is at position 6, 7, 8, and 9, and record in a bipolar fashion from those electrodes, and the recording from those electrodes were to look like I have just introduced in this frame, the assumption that we previously made regarding the frontal positive field would be wrong. The correct assumption would be that we're dealing with a negative field with maxima under the electrode labeled as 4. When faced with a recording with the largest amplitude wave at the end of the chain, the best remedy is to go to common referential electrode montage. Another pitfall to avoid when looking at bipolar recording is to misinterpret an equipotential zone at the end of the electrode chain. This situation may lead to erroneous lateralization. If we encounter this tracing, as I have put on the right side, we could assume that the left side is significantly different from the right. We could assume that there is a significant depression on the left side of the recording. Yet, if we add additional electrodes, as I have done in this frame, and record in a bipolar fashion, we would then record waves not previously recorded because we have expanded the field of recording. This new wave would allow us to conclude that such asymmetry is not present, or at least that the asymmetry is not as prominent as we thought before. Another pitfall to avoid when using bipolar montage is to misinterpret the wave geometry and the frequency when evaluating a monotonous tracing. A tracing such as this one may be recorded when electrodes are being used too close to each other. The remedy is to increase electrode distance or to use common reference montage. So the answer to this question is A, all of the above. Next question. A flat EEG using regular bipolar montage can be used to determine brain death. A true, B false. This frame shows the technical recommendations that must be met when diagnosing brain death. Take a few seconds to read them over. I especially like you to pay attention to the 10 centimeter rule. I think the rationale for it is that a potential will increase up to 10 centimeters from the source and then start decreasing. Yet, placing electrodes 10 centimeters apart in a 35 centimeter head circumference, as we often find in neonates, is not easy. Be it as it may, one thing is sure, that bipolar EEG recording with closely placed electrodes is no good to diagnose brain death. In such cases, a referential montage is by far more appropriate, and as it is shown in this case, it may reveal isolated activity with equal distribution and amplitude, or even a significant amount of activity with perfect synchronicity and correlation. So the answer to this question is B. I'd like to conclude this talk by telling you about both sides of the street regarding bipolar montages. Bipolar montages are good because they have robust spastical filtering effects. That is, they are good to detect and localize highly localized potentials. Bipolar montages are good also for removing widespread waves with similar phases. Bipolar montages are good to visualize wave with highest definition, and bipolar montage are also good to detect low to medium amplitude waveform that are highly localized, as I have already mentioned, but this is a point that is worth repeating. And finally, bipolar montages are good for source localization when longitudinal and transverse montage are used in combination. Bipolar montages are bad for certain things. They are bad to detect hemispheric asymmetries, that is interhemisphere asymmetry, unless, as we have just mentioned, we combine longitudinal and transverse bipolar montages. Bipolar montages are bad because the amplitude of a wave indicates the slope gradient of the voltage zone that the electrodes are placed and not the real amplitude of the potential. Bipolar montages are also bad because the wave geometry is distorted and jam frequencies may occur. And finally, bipolar montages are bad because deep fields are not duly represented in the recording. Thank you very much for your attention.